Okay, welcome everybody. So this webinar is about to start now. We will have closed captioning, live transcription in CC available by clicking the CC button in the bottom bar. And at the end, we will have questions, time for questions. So if you have a very burning question, you can ask it during the presentations, but preferably leave the questions until the end, since we have a quite tight schedule. You can also add questions in the chat function, or when you want to speak, just raise your hand, so you will be called by the moderator. And this webinar will be recorded and available for viewing afterwards. So our title today is Human-Driven AI Solutions for Access and Manage Audiovisual Content, a Research Perspective. And we are MeMAD, Methods for Managing Audiovisual Data, EU Horizon 2020 project that is finishing in a couple of months. The partners are Aalto University from Finland, University of Helsinki from Finland, Eurecom in France, University of Surrey, UK, YLE, the Finnish broadcasting company, Limecraft, Linksoft, and Institut National d'Audiovisuel from France. The general goals of our project is to create novel tools for digital storytelling. And by this, we want to expand media audiences and understand multimodal content analysis and consumption, and also to improve formal models and languages to describe audiovisual data. The program for today is here. So our first speaker is Jorma Laaksonen, who is talking about advances in automatic audio description and of audiovisual content. Then we will have Sabine Braun from Surrey University, and then Raphaël Troncy from Eurecom, and finally Jörg Tiedemann from University of Helsinki. My name is Mikko Kurimo. I'm the coordinator of the project from Aalto University. So without anything further, so I would call Jorma to start.
Yes, hello. So I'm Jorma Laaksonen from Aalto University. I've been leading work package 2 in the MeMAD project, where we have done automatic description analysis of multimodal data audiovisual content. So the aim is to use all available cues that we have from the visual and auditory contents of the media to describe it. Each modality could be described separately, but what we really want is to describe all the modalities together, and in a way that it is as close as possible to the ways how humans would describe the same content. I'm visualizing the process with this card where the automatic multimodal content description is in the middle and all the input modalities or input data sources are surrounding it. The starting point is a visual video captioning that tells something about the content of a short video clip. For that purpose, we have used our Aalto University's own development that is known as the deep caption code of the PIXOM development group. We have participated in a number of evaluations with that code, most recently last year's TrekWith 2020 video to text task, where we scored quite well among the best participants, at least with respect to this blur measure that is used for automatic evaluation of visual captioning. The methods that we use are quite typical: long short-term memory model with different databases and features used in training the model. The next part here is the face recognition part that is development from Eurecom. The emphasis there has been mostly on automated finding of reference images for known persons. The face detector model is MTCNN, and then FaceNet features are used for face recognition. Evaluation that I'm showing here has been carried out with the MeMAD project's own selection of TV programs. It shows here that there is a number of persons whose names are given, and then the system has been able to find reference images of those persons and find their appearances in a test set of videos with some precision recall F-score to show that the system really works from no human intervention. The next part here is speaker diarization that gives its output to the system. It's development by Linksoft and Linksoft language services. The aim of speaker diarization in general is to separate speakers from each other and from the background music. It has been developed in multiple stages. The latest one uses this ASC-NME model that is auto-tuning spectral clustering with normalized maximum item cap. Evaluation shows here for two languages, Finnish and Swedish, that the diarization error rate has gone quite nicely down during the project, and it is now in a very good level. Then we bind the speaker diarization and face recognition processes together so that for this example that I've been showing here for a kind of a hypothetical movie that could exist, the system is then able to know that speaker number one might be associated with this person name because the face appears together with the spoken with the speech of a person, and similarly the other speaker is associated with another name by the co-occurrent appearance of the voice and the face. So with this process then we are able to replace the references to a man and to a woman in a caption with their proper names, and even if somebody is not visible but we hear the voice of a third person, we are able then to name that the third person is appearing. In this slide, there is a short brief comparison of or evaluation of the method, and we can see that at least for some program types, the accuracy of the person name is quite accurate, whereas in some cases where there is news programs where there is a kind of an invisible journalist talking but not visible, then we are bound to lose information about that person. The speaker diarization can also be used as an input tool for the spoken language identification. That is a work carried out in Aalto University with a language embedding model and a simple naive Bayes classifier for 5 languages. We have obtained results where we have been able to name the language that is spoken in correctly for 88 or 59% of times in 2 example programs. So each speaker turn is identified the language separately. So even if the same speaker changes the language, we are able to detect it. Then comes audio background recognition that is based on a neural network model that uses the BGG's audio features and a model with multi-level attention. The data that has been used for training it is the Google Research audio set with 527 different audio content types, and this table shows that the mean average precision could be very close to 1 already with this method. The final thing on this diagram is then the scene recognition part, which has been a quite ad hoc implementation of visual scene recognition using the data from the SUN 397 dataset, ResNet visual features, libSVM with radial basis function kernels. We can see again that for some program types, the scene recognition works quite well, whereas for some other types, it's not working that good. So finally, when we combine the inputs from all these modalities together, we are able to create sentences that describe the video shots, mentioning both the names of the persons, where they are, what are they doing, who is speaking, what language is being used, and possibly what is the audio background that is heard simultaneously. So finally, this automatic multimodal content description is a combination of the modalities. There are some post-editing rules that are applied to the caption so that the caption takes the other information modalities into account. So a sentence that starts as a caption as a woman is walking down a street and talking can be converted in post-processing to be in a crosswalk. Marit Åström Kupsonen is walking down the street and talking while music is heard. Two short example clips. You don't need to hear the audio. You can see here that it is mentioned a car driving. In a caption, it mentions a place in a crosswalk. It mentions that somebody will be speaking soon and that there was a music in the background. Another shot inside the car mentioning the person who is visible. And another short example mentioning two people who are visible, mentioning third person, and then gives quite a good description of the visual content of these shots. So what we would still like to improve or do in the future, all these inputs are prone to errors, and that's why also the multimodal description is very prone to errors. It's difficult to get all parts of the description correct simultaneously, but on the other side, it's easy to get at least one of the description correct. Now the descriptions are always applied to short visual shots of something like 3 to 10 seconds, but of course we would like to get also descriptions for a longer span or longer duration of the content. And then we would like to combine also the results from automatic speech recognition to this. So very often the caption says that there are two people talking about something, but I would like to see that we be able to know that they are talking about their traveling plans or something. So in that way, we could add still one more modality in the description if we would tell what is the topic of what the people are talking about. So this was my presentation. Please ask questions later after the other presentations.
So we could go directly to Sabine. So thanks, Jorma. Can you, Sabine, share your slides?
Yes, I will. Yep. Okay, can you see me sharing?
Yes, looks good.
Okay, so hello, I'm Sabine Braun. I'm from the University of Surrey, from the Center for Translation Studies, and I work mainly in human translation studies, I should say, and especially I've been working in human audio description, so the description of audiovisual material for blind and partially sighted people. This is how I came to this project, because in this project we certainly focused on also combining machine and computer vision work with human input. And so my presentation will focus on this role of human input in audiovisual content description, video scene description. So I want to give a bit of context why we started out this way, and also link it back to Jorma's presentation. So I will take you a step back, and later on then you will be able to see in principle implicitly how far we have come, because I want to step back and say what video description was like before we started the project, and then relate the work that we've been doing. So I will have a very quick comparison between human and automated descriptions, and then talking a bit about how modeling human processing of audiovisual content actually works, and what we have learned from that in our project, and what our sort of recommendations have been within the project for next steps in automating this. And in principle, the sort of recommendations are the ones also that Jorma and others have taken up. So much of what Jorma presented is in principle an outcome of our joint work of all of us in the project looking at this. So just to say, I mean, why do we do this? Yes, the multimodal content revolution is all upon us. And I wanted to emphasize here also that this has led to quite a number of different user requirements. And in our project, we have always looked at both. On the one hand, we have looked at how we can make content manageable and accessible for retrieval and reuse for archival purposes, basically in broadcasting archives. But the other more longer term goal was also always to bear in mind how can these methods that Jorma has outlined, the machine description methods, one day perhaps be applied to support and facilitate the production of descriptions for visually impaired people. So to meet this demand, of course, automation has begun in this area, and our own goal in the work stream that I've been responsible for was to sort of improve understanding of how human descriptions work, carry out a comparison between human and then available machine descriptions, identify differences, identify areas where human input could be used to improve the machine output. And so basically building human-based models of audiovisual content descriptions that can be, if you like, translated into what a machine can do with it, and the people who develop the algorithms for the machine, of course. I believe many of you will be familiar with such examples, but here's maybe one of the examples of the type of sequences or that you get description sequences that you get when you ask a machine to do this, or at least I should say that was at the beginning of our project. So you would see on the blues are the relatively sparse descriptions that were produced automatically by the tools that were then available, whereas on the right-hand side is a description that has been produced by a human being. Clearly you see the difference with the machine descriptions being produced on the basis of training data of large data sets and algorithms, feature extraction. And these data sets at the time had the disadvantage that they were mostly based on static images and small animated GIFs, but not really video description training data yet. And of course, then there are many other problems with these with this description method and the training data that we have looked at. So maybe one of the also interesting sentences that we come across is here that the description that the man is cutting a banana, this caused amusement, I think, throughout the many years of the project. But how does it happen? Of course, it's all based on amateur descriptions, as you can see exemplified below here from the MS COCO data set. Which contains just over 45,000 times the word banana, but obviously the matches are less than correct. And what we have looked at the training data sets, we have analyzed them also to get behind what are the real issues in the machine descriptions. So we can see there are a number of methodological issues, of course. This is crowdsourced material. That means the actual descriptions have also been made for a different purpose, apart from the fact that they are descriptions of static images, mostly different purpose, not necessarily professional describers, but rather volunteers who provide a rather sort of amateur description. They are quite ephemeral. They are quite, I don't want to say superficial, but we have carried out corpus-based comparison between sort of the linguistic consistency of these machine descriptions and the human description. So you see there's lexical poverty. I think we found 5 verbs that are mainly used to label actions, and also a small number of recurrent, very generic nouns that are there. So there's generic material. There's also a high degree of inaccurate material still. There is, of course, because it's all single frame descriptions, there is at the moment a lack of temporal cohesion markers, for example, in this material. So those are the things we have tried to establish. Then there are many computer vision issues that had to be, and that in the project, of course, have been addressed with character recognition. Jorma has already explained some of what has happened there, gender identification issues, object identification issues related to sort of changing on the scale, changing the perspective. Also given the fact that there are many non-iconic images in these video descriptions, of course, and yes, the linguistic issues I've commented on. And of course, also we saw quite clearly that there is a total lack of integration of other modes in the production of these video descriptions. There wasn't any integration yet much with audio cues, vocal profiling, speech comprehension in any way. And this is, of course, partly been the work of MeMAD to look at this integration and to see how we can improve this collectively. So then I just want to jump quickly at very brief overview of okay, how do human beings do this? And there are many well-known theories and models to describe how human beings process not only audiovisual but generate text, but also audiovisual or multimodal input. The great ability that human beings have, and that distinguishes, I think, us from machines at the most, we see the bigger picture. So we have an ability called mental modeling. We are able to process the input that we get from bottom up with what we already know and general knowledge top down. So in this continuous combination of activating our top down resources and taking our the input, visual, verbal, audio input, and this ability to combine these connected to our ability of making reasonable inferences about what could be meant, and our ability to then also take care of the finer detail by picking out what in an audiovisual content is actually salient and narrative for that particular purpose. Those are all things that distinguish us currently from what the machine can be doing. So we are able to see the bigger picture, but then drill down to the finer detail, filter this for relevance, if you like. And of course, we also have the ability to identify narrative schemata. So we have knowledge about how stories are normally told. That also, and that is another part of the puzzle that provides the context that human beings have in order to understand contents or audiovisual stories, if you like. And so in our attempt to model this a little bit for, because this is of course all relatively abstract, but in our attempt to model how this could look like in a format that we can begin to pick up and learn from to make it, if you like, machine compatible, we've tried to illustrate the different layers. So I think what human beings do, even though I would have to say it's not, I don't think it's really step by step, but of course we have the ability in the first place to identify the key elements in a story, the characters, the actions, the locations, perhaps the mood, the objects that are playing a role in it. And at the most basic level, this is of course something a machine can already achieve, and that has also happened before MeMAD. I think that machines are able to do that and to automate, if you like, even tagging of content via keywords in that way. But then if you go at the next level, what I've labeled your content description, which we think is sort of a plain description of what you see, no interpretation yet. So I think this is the status where in the MeMAD project we also picked up on, even though we had to say that those content description themselves had all the issues that I mentioned before. But that's at least sort of the first step of a description which could be used in archival for archival purposes to begin with. We are talking about what can make a start here, obviously. Then we go at the next level where we can perhaps begin to talk about how an event narration is formed in the human mind, where interpreting the content, establishing cohesion, establishing causality, consequence, inserting temporal sequences, markers, how this comes about, where we don't just describe what we see, but where we begin to explain this a little bit. That is, of course, still, I think, where our work in MeMAD is also situated at, and that is a level to aim for over the next years. Then when it comes to actually recognizing and then trying to replicate these story grammar type models, if you like, that tell us the blueprint for how a narrative is actually structured, with an initial sequence, with sort of building up the suspense, if you like, actions after actions and coming to a resolution. That is yet much more difficult, although we have in our latest step in MeMAD, we have begun to identify those narrative elements in short sequences of videos and video clips up to 2 minutes, and one of the final parts of our project will also be able to see whether something from that narrative sequencing, whether it's reliable, whether human beings identify this reliably, and whether something of that can then be used to begin that narrative sequencing in the machine. But that is very preliminary steps, I would say, and this will take longer than the duration of the MeMAD project to continue with that. So the steps we have identified, to wrap this up, the steps we have identified over the months of the project that could perhaps be addressed in the computer vision and machine learning development to come to automated or at least semi-automated descriptions are the ones that I have listed here. Basically, we've discussed a lot in our project how character identification can be made more efficient by improving it by using face recognition, voice diarization, and this is indeed what you have also heard that Jorma presented, and that has now become fully part of this work that our colleagues are doing. Intelligent object recognition we have discussed, so basically to enhance the sort of a more contextualized object recognition, which is more sensitive to things like scales, aspect. Of course, that also depends on what kind of training data sets are available. We discussed action labeling, how this can be advanced by, and how the precision can be improved there by, for example, maybe combining topic detection techniques and with sort of a richer and a more relevant lexicon behind it. And I would add that our role in the project has always been to make these suggestions. It's perhaps also for a non-technical person easy to say this, but I think we have been successful in taking these up in the project and moving this forward quite a bit. So temporal sequencing was another narrative saliency. I've just commented on that. I think that is still very much work in progress, and sensitivity to sort of this whole narrative paradigm of storytelling, that is of course also a step that needs much further work. But I hope that the two presentations that Jorma gave, Jorma has outlined you the perspective, how far we have come in this area of the project, whereas I was sort of backfilling this a little bit and showing you how, to some extent, how we got there. And I hope that's what I have achieved, and I'll hand it back to Mikko. Thank you.
Okay, thanks, Sabine. So I propose that we now immediately go to Raphaël's presentation. So please.
Sure. Good afternoon, everybody. So indeed, Jorma has shown a lot what the machine can automatically do, while Sabine was presenting and emphasizing the needs for human inputs. And I will be in the middle here, trying to show you how we can leverage knowledge graph and human inputs for really improving automatic media understanding. So in MeMAD, we start with content providers, which are INA and IDE, who start by providing media content, in this case, TV and radio programs which have been broadcasted, together with metadata. Those metadata, they are human-made. This is Documentalist, which generates descriptions of those programs and those program content in particular. Of course, they follow guidelines and best practices in documenting this in the spirit of being able to find excerpts of documents in the future by querying archives. The problem with those metadata is that they all come with different format, different level of granularity, different languages, of course, but they have also commonalities. They describe the broadcasting moment, the genre, the channel, and a number of relevant information. So one of the steps we have made in MeMAD is to promote this EBU core data model, which is an ontology that describes those commonalities across broadcasters. And we have been able to be one of the first implementer of this model, producing one of the largest knowledge graph of TV and radio program broadcasts. So this is an excerpt of what you can see here, a particular program which will be decomposed into parts, which have been broadcasted on a particular channel at a particular moment in time, and that can be part of a collection, etc., etc. On top of this knowledge graph, we have built an exploratory search engine, which is called Explorer, available at this URI. Behind use a password though, so you need to ask us if you want to have access to it. But that enables to browse the channels, the collections, and to see all those programs that have been made available to the MeMAD consortium. And you can start filtering them by genre, by a number of the people appearing in those programs, etc. And at the end, you can really watch particular excerpts, but also have access to automatic metadata that have been produced for those parts or programs, and even have suggestions of related content that I will not be able to go further on this. So what I was saying is that those programs, of course, and those parts of programs are about topics, about things. When you're, as a human being, you read a textual document, for example, the one on the left here, and your eyes immediately pay attention to some particular terms, you immediately understand as a human being that this document is probably about sports. While on the right side here, we have an automatic transcript of this TV news. And in this particular, if you understand French and you can read those keywords which have been highlighted, you will understand that this parts of the program is probably talking about economy as a general topic. Now, how can we teach the machine to be able to extract automatically those keywords and those general topics that would be useful to categorize the content? So Meet Tomodapi, this is one of the project results in MeMAD, where we have built a Python library, and it's also an API that is basically a wrapper around multiple topic models that have been proposed in the literature over the last 20 years. It includes already 9 different algorithms, together with a lot of evaluation metrics, and that can be optimized for your particular use case. So there are more details about this work in those links if you're interested in. And why we are all doing this is because at the end we wish to be able to support the human being in automatically segmenting and categorizing the media content that will be searched or reused in the future, which requires to find what's the right unit of content. You know that the media can be decomposed into shots, but the shot is really mechanical in the sense of what the camera has captured, but it's not really what the appropriate unit that the human being is looking for. So again, let's go back to what humans are doing. Given a particular program, this is what documentalists are doing. For example, in the French National Institute of Audiovisual, they are decomposing by hand the program, and they are attaching to some of those parts titles that corresponds to what those parts are about. This is what they also call content description. Now, in parallel to that, there is the entire audio and speech of the presenter that can be transcribed with automatic speech recognition technology, where you have each sentences which are time-coded, so to speak, with the video. And one of the tasks we wanted to do is, can we associate a number of sentences from the ASR to those content description items that corresponds to meaningful units for the human being? So we developed a method here that basically consists in chunking the program into the smallest units of content that could be short or could be ASR sentences, and then generate vector representation for those textual units and content descriptions, in this case using sentence birds, and then computing a similarity matrix between each description and chunk vector representation in order to cluster successive units of high similarity into segments, those segments we are looking for. We have applied this method to documents in the MeMAD datasets with very encouraging results. Sometimes we can find this alignment between the content descriptions and the ASR, and sometimes it's much more difficult because in this case on the right side, we don't have this nice diagonal that we are looking for, because the entire emission, the entire program is about sports, and sports terms are mentioned all the time. So it's much more difficult for the machine to clearly distinguish when we are switching topics, because all topics are sports related. So this shows the limits of the approach. Now, I had a good case where we had these content descriptions, but in many cases, the documentaries don't have the time to even segmentate the program and provide content descriptions for those items. So can we automatically infer them just looking at the ASR? So this is also what we are trying to do. And again, sometimes with encouraging results and sometimes where it's much more difficult. Finally, I would like to conclude this short presentation with imagine that you have no segments, but you would like to understand which segments from the programs are the more interesting. How we would call them very interesting moments, and how can we leverage on the multiple modalities to find them? So formalizing what is interesting is, of course, very difficult because it's highly subjective. And that can refer to, there is this nice survey which had been published 2 years ago, which tries to formalize this concept because it's related to aesthetic values, the notion of whether the scene will be memorable in the future, and many other parameters. In Medieval, which is a international benchmarking competitions, they have created a task actually, where given a set of medias, your task is to predict whether this particular video scenes will be memorable at short term or long term. And again, here we ask humans to provide inputs, which is to provide a score, whether they believe that, or we compute a score, whether the scene that they are watching, they will be able to memorize them a few hours after watching them, or even after a few days. So the long-term memorability score. So again, we have participated into this task using an original method where we use an analysis of all modalities. So we use, of course, the visual modality, but also we enrich the video with content descriptions that we're automatically generating using what Jorma has proposed. And using both the textual and the visual inputs, we train then different neural networks, and we aggregate the score into predicting whether the videos will be memorable or not. We participate last year in this competition, obtaining the second best results, and we also participate this year, complexifying a bit more the method, adding the audio features and also visual linguistic models, and this year achieving the third best results. So in summary, because I think to conclude now, in this work in MeMAD, we have published one of the largest TBU core-based knowledge graphs describing radio and TV program, where we have tried to also integrate results of ASR, automatic multimedia analysis, face recognition, machine translation, and even name entity recognition. We have developed an exploratory search engine for searching and browsing these large collections of content. We have developed a library that enables to extract topics, including numerous topic modeling algorithms, and that can be optimized for various use cases, depending on the nature of the documents you need to analyze, whether it's a textual document, a news article, or a transcript of a video. And we have tried to develop a multimodal method to rank what are the important moments, understanding that this is a very subjective thing. Now, what we also observe is that it's very difficult to generalize. So generally, what you train on, given human input, can to some extent be extrapolated for other similar contents, but it generally is not as effective when you completely change the topic or the genre of the documents, which means that there is still a lot of new research to conduct on this topic. On this, I'm happy to pass the ball now to the next talk.
Yes, thank you very much, Raphaël. And the final talk before we go into the discussion part would be by Jörg Tiedemann. Please.
Yes, hello, thanks. Thanks for staying in the webinar. So the last presentation in this webinar will be about the cross-lingual information access, which is also very important, as we have already seen quite a lot of different languages here in the presentations. And part of getting information is, of course, also being able to read things or to access information in different languages. So in MeMAD, we had this specific work package that was dedicated to the development of machine translation with the aspects of accessing information that comes with audiovisual data. So here we have the summary of the objectives in this work package, where we wanted to focus on especially multilingual models, so focusing on lots of support for different languages, but then also in the multimodal settings, so that we have different kinds of multimodal input that we can handle and take features from. Of course, we would like to develop state-of-the-art techniques and models, systems that can practically be used. And there's a lot of new developments in the recent years with the rise of neural machine translation. And then one other special thing that we want to focus on is also the effect of discourse and contextual information, how that influences the quality of translation that we can achieve by automatic means. So how can, for example, stories that really depend a lot on the context get information from extended contextual information? And finally, the integration into all the different types of systems that we develop should also be tested. So in the system that we develop as a prototype, we also would like to see how translation can be used for practical purposes like content retrieval in media databases. So those things were the objectives, and let's see what we have done. Here, just quickly to remind you about neural machine translation, which is now kind of the state of the art and the common approach, just giving you a bit of an overview how this typically works. So we have these kind of encoder decoder models that try to resemble human language understanding, human language generation, but in connection with neural models that are trained on data. So those models that come in different kinds of architecture and use lots of different kinds of technology, they try to map observable language into some latent semantic space, reflecting the meaning that is behind that language, and then trying to use that to translate it or to generate something in a different language. So this has been very successful due to all the kind of additional computational power that we nowadays have, and also data sets that we can have available. But also especially this abstraction level that models can achieve is actually quite astonishing. So I don't go into all kinds of technical details here, as this would take too much time, but just give you some highlights of what we have been working with. So as I said before, we would want to focus on multilingual models, meaning that instead of just having bilingual translation models from one language to another, we would like to focus on integrating many languages in just one model, taking advantage of the similarities between languages, making it possible to have cross-lingual knowledge transfer between those properties of different languages, but also focusing on getting systems that really make stronger semantic abstractions by making the task harder for the machine. So assuming that if you have a lot of variety to translate, that you also push the level of abstraction that a system can achieve. So with this, we have continued collecting a lot of data. So there's this Opus corpus that maybe some of you know, which has a lot of different material available that you can use for training. Among others, it has really a large subcorpus collected movie subtitles translated into over 60 languages. So quite a nice resource for this project here. We have developed a model that we explore in this project, among others, where we want to focus on this multilinguality, this aspect where you can connect many languages. And the model looks from a high-level view like this, that we have one shared component between our languages, and then we have language-specific encoders and decoders that take care of reading different languages and producing other languages. And this shared layer then in the middle would then create this kind of meaning representation that we need to get to a language, more or less language agnostic representation in the middle. So this is one of the models that we have explored in the project, and we have seen that this approach leads to some interesting aspects that we can see in translation. For example, that multilinguality really helps translation performance. So if you throw these languages together in one big model, then it outperforms the bilingual models that you otherwise get with just training those two models. So it doesn't see more data for those two languages that you test on, but the different aspects of the other languages push the performance of the system, as you can see here with the red bars on the top. Another thing is also that you can actually translate between languages where you don't have any training data in the training sets available. This is called zero-shot translation. So you can translate between those language pairs through the intermediate semantic representation layer, even though you have not seen them in training. So this is nice. Another nice thing about this model is that you can actually also include rather straightforwardly other modalities. So instead of having just language encoders on pure text, we could also have, for example, speech encoder of some specific speech input, so audio-based input. And this is what we have explored also in the project. Just to zoom in a little bit, again, there's some details that I'm not able to explain here because of time limits. But if you have this kind of what we call attention bridge in the middle, and then you have, instead of textual decoders, you can also have a specific audio encoder that takes an audio stream, transforms it into the same kind of representation that will be linked with the other language decoders. Then this can be put together in this global system where you can iterate over all these different combinations of text-to-text translation or audio-to-text transcription if you want so, or also from audio input to foreign language text translation, for example. So this is what we have explored in some of those studies. And here you can see our contribution to a competition on speech translation from last year, I believe, is this slide. So where we try to explore that model for multitask learning, where you then can have different tasks of translation from text English to text German, but also audio English to text German, and have all these tasks integrated in one big model. And then we can explore how those different tasks influence the different abilities of picking up translation performance. Now, this is the kind of disappointing slide, which this is still kind of ongoing work. It is really quite a hard task and quite new to actually do this end-to-end translation from speech input to text output. But we can see that those different multitask setups really push the performance from the basic training baseline to the output that we can see with different tasks integrated. And this is, as I said, ongoing work. And these blur scores, if you know what blur is, then this looks very low, but it gets to some promising ideas that we would like to explore further also beyond that project. And we can discuss this more in discussion if we have some time for that. So let's move to another modality we have already seen in presentations before by Jorma, the image caption generation or caption generation for video content. We also participated in this task of image caption translation. So not only captioning, but also translating those captions to different languages. And here the basic task is to actually take captions that you have for an image and try to translate it, but include also image features to improve the translation. So this is actually not a good example because the image is not really necessary to make a proper translation of the inputs that you have given, but the idea is the same, so that we explored different ways of integrating features from the image. One is to use Jorma's tools for generating captions, so you have auto-generated captions that you can concatenate with the given input for the image, and then try to translate that in connection with the input that you have. But then the final system that we actually submitted to the system, to the competition, was that we extracted visual features from the image and then included the feature information in the decoder of the translation system to give the system additional information that only comes from the image. And this ended up in our shared task contribution 2 years, so almost now, well, 2.5 years ago. And we participated for the first time, and it was a good project success here, where we had a collaboration between different partners in the consortium, and we had by far the best system performing in this task, whereas other teams were working on that task for many years. So this was basically a surprise for us, but kind of a nice, interesting outcome here that we performed on a much higher scale in this task of image caption translation. So this was English, German, and English, French, and details we can also discuss later if you like. So final point, because I mentioned also discourse-aware machine translation, so extending the context in machine translation, which is really important, as we know that everything is contextualized if you use languages, and especially if you have stories and stories connected to videos, the context is an important factor for disambiguation and so on. So we tested that with context-aware machine translation models, where we basically extended the input to have more than just one single sentence, but instead of that having several sentences as an input. So trying to extend the context as much as possible and seeing what is the effect of doing that. Now this is quite of a very confusing slide possibly, but here you can see that we compare subtitles in this task to news on the right hand side, and we can see when we compare context-aware models where we have more context available to ones that that have confusing context just to make the test, then we can see that the context really influences the system quite a lot. So we lose a lot of information if we don't take that context into account, and this analysis gives us the hint that we should really take care of contextual information, especially in the subtitle case. So with this, just summing up, we have done multimodal machine translation in various ways, doing speech to text translation, but image caption translation. We provide all the resources publicly available. You can see the link at the bottom of the slide. So you can get actually the models, but also our systems. You can also get the data from various links that we also provide there. We have benchmarks, and you can explore all these things by yourself. Yes, and with this, I just hand over to Mikko, who will moderate the questions. Thank you.
Okay, thank you very much, Jörg, and all the speakers. So we still have some time for questions. So please, use the chat function to comment or raise your hand so that Mikael can give you the floor. The presenters can also ask questions from each other if you have something in your mind. I could start by asking Jorma that what kind of practical use case would you have in your mind for this kind of methods, and what would be the important kind of performance metric in that use cases?
Use cases such as searching and finding content is not good ones for this. I think kind of a traditional indexing of single modalities is much better than trying to combine the modalities together for indexing and search. So I guess the main use case is for content description for people who have limitations in knowing or seeing the content by themselves. Of course, the quality of the descriptions is still quite low for that audience, but anyway, I think that is kind of the ultimate goal in some way, to aim the descriptions for those who are lacking the ability to see.
Okay, there's one question.
Perhaps can I comment on that, perhaps?
Okay, sure.
Also to make sure I totally agree, Jorma, this is a long-term goal for those areas where, especially, of course, for those areas where at the moment we have professional human describers, they can do this job better. But I think we also want to bear in mind that there are many audiovisual areas. That's why I was talking about this audiovisual or multimodal content explosion, if you like. There are many areas where no professional content describer, audio describer would ever reach out to, because there is no resource for that. There's no resource to pay. So social media, YouTube, what have you. And I mean, in those areas, we can indeed look at whether automation can facilitate that there. So I think we should also make it clear we're not in the business of verbs at the moment replacing those areas where you have competent human describers, but to look at additionality and what other areas we can cover with that, where in some cases a description is better than no description at all.
Yes, there's one question from the audience that how much processing power and memory these solutions require.
Yeah, that's for you guys.
So maybe for Jorma and Jörg, maybe at least your answers might be most interesting.
I don't know who wants to start, but well, of course, it depends a lot on the data size and the models that we use. But as most of these things are driven by some deep learning neural networks, so the training is typically quite heavy. So training procedures for most models will require quite a lot of processing power and memory. For applying them, that might be slightly different, but also that, of course, can be expensive. I know that our machine translation models, at least, they can run on CPU servers. We have these demonstration translation servers that run quite well on CPU, on just general hardware. So that's on inference time, I think it's kind of okay. But I guess this really depends on how the integration of different modalities also comes into the picture. Right, Jorma?
Yeah, we don't have very accurate measurements about the current status, but in kind of a design principle we have had that if we would sample one frame of the video every second, we could analyze it in real time. And now if we have kind of a shot-based approach, like in what I was showing, the shots are typically something like 3 or 5, 6, 7 seconds long. We need some processing power also for the shot segmentation, but that is not very much. But then if we pick one frame from each shot, then we could get quite close to real-time processing, if not necessarily with one CPU, but with one computer which has a bunch of CPUs.
And there is a question to Raphaël about metadata tagging. Are you ready to answer?
Yes, I can answer. Thank you for the question, Valentina. So I have been very fast in presenting, but we have done a bit more work on this in MeMAD. So there are various sub-problems, so to speak. What I have briefly presented here is with Tomodapy, is really topic modeling in the sense that it's completely unsupervised. So you provide content and basically you just tell to the algorithm how many topics at the end you expect to see your documents be classified into, and you let the machine do it by itself. So of course, this is quite challenging, and what you obtain at the end is it's even difficult sometimes to phrase the topic because it's a lot of terms that characterize pieces of content, and generally it requires another iteration of human input to fully understand what the machine has wanted to do in separating this content. So it's still content tagging, but generally it requires additional human input. On the other side, what we have tried to do in MeMAD as well is what we call topic categorization. So here, you know the output, you know what you want to have at the end. That could be, for example, a broad list of topic labels that you provide as input to the algorithm because you wish to categorize, for example, your content into 10, 20, 30 topics for which you can provide a label. And in this case, the problem is more a classification problem. And we have very, very good performances, including with no training data. So in a zero-shot setting. And here again in MeMAD, we have demonstrated that thanks to the recent progress in language models, we can properly automatically tag content as soon as the input content description is of good quality.
Okay, and the interpreter asked for the question, so Raphaël was answering. So how far we are from the complete automation of tagging unstructured audiovisual content?
Yeah, sorry, I should have done this. So automatic content can go a long way.
I could have a very short practical question to Jorma. So for example, if you recognize names of persons in videos, of course, in movies, you would like to have the character name in that movie. So how well could that be interconnected with plot descriptions of a movie where those names are then connected to the actor, so that this kind of then becomes consistently the name of the character in the movie instead of being the actor?
Yes, of course, in most movies that is a very simple one-to-one replacement, but there are of course movies where the same character is played by a number of actors, or vice versa. One actor is playing a number of characters, and I guess everything in between is possible in movies, so it depends.
So what would Jorma think about cartoons, for example, or some animation where there are no humans talking, but some animals or objects? What would happen there?
I haven't thought about it, but I guess the association between the voices and the faces is very simple co-occurrence in the media, so possibly it's possible to learn also the voices of the animals and trees and other plants that happen to speak in cartoons.
We could still take one more question if there are any. Time is up, but it's not so strict. If you have any things in your mind.
Well, perhaps we can add this point, because I think that the point that Jörg sort of raised again, I think that's been something we have discussed a lot in the project, and I think at least in the earlier stages there has always been the issue of the sort of, if you like, re-recognition of the same character throughout a video sequence, and that's, I believe, still problematic if that character is shown from different perspectives and from behind and from the front. So I mean, the first step is still that the machine has to actually recognize that it's the same person going through different video scenes before this whole name matching can actually happen. And I think our hope in the project was that by pulling in these different modes, voice recognition, so that this can then be improved. Maybe we can make a final comment on how far we think we've come on that. You know, so what this, because this was something we set out to do. So how far this whole multimodal integration has actually enabled us to come a little bit further in resolving these issues. That would be a question for Jorma, I suppose.
Yeah, I wasn't sure whether it was a question or philosophical consideration, but yes, I agree that that is a question that we set in the beginning of the project. It is a direction where we have went during the project, but not reaching the goals that were set in the beginning. Of course, the goals are always to some extent at the horizon of the visible world. So we are not getting where we aim, but we are getting in the right direction. Difficult to measure what is the fraction or part that we have done of the work that we thought that would be the aim towards the goal. But I guess there are multiple facets of the work progressing independently of each other and also progressing together. So I guess there has been no area of the work that would not have benefit from the project. So we have made progress in all fields, but very seldom, of course, reach the original goals fully.
Okay, I think time is up. So I just advertise our next webinar. So next Tuesday at the same time, we will talking about industrializing media production from a producer's perspective. And again, same organization as this one.